Hello everyone, my name is Srinidhi Narayanan. I'm a PhD student in the Department of Mechanical and Materials Engineering. Today, I'll present a paper titled Towards a Design Space for Emotion Recognition. The author is Vivian Gennaro Morti, and the paper was published in UBComp ISWC in the year 2021. This paper gives a broad view of how emotion recognition works in interactive systems. The field is very rich. In fact, it's my PhD research area as well. We have psychological theories, sensors, platforms, and machine learning models, but they are often studied separately. So, this paper tries to bring them together in one place. So, it creates a design space. A design space is like a roadmap. It helps us understand and lets us see the whole landscape and to see what choices exist when we design an emotion recognition system. So, in this talk, I'll explain the main ideas from the paper. I will also give examples and highlight strengths and weaknesses. My goal is to make this topic simple and clear. So, moving on, the paper talks about its motivation first. So, emotion recognition is becoming very common in interactive systems. Many fields use it. Mental health is one such example. There's also educational softwares, cars. So, educational software uses it to understand student engagement. Cars use it to monitor driver stress. Assistive technology uses it to support people with disabilities. Even simple everyday systems like phone, wellness apps rely on emotional data. The problem is that research on emotion recognition is all scattered. Different groups use different sensors. Some studies rely on facial expressions, whereas some use speech. Some use physiological signals like heart rate. So, what I'm trying to say is that there is no unified approach. So, because of this, it's hard to build reliable applications. It is also hard for new researchers to know where to begin. So, the author argues that we need a clear design space. A design space helps us compare methods. It helps us understand what sensors fit what situations. It also helps us evaluate trade offs. So, that is why the paper focuses on giving a structured overview instead of presenting a new model. You can imagine this like entering a huge supermarket for the first time. Without labels, all the shelves look the same. The design space is like a set of signs that tells you what each section contains. It makes navigation easier. So the paper begins by describing a common pipeline for emotion recognition. So the first step is data collection. So we collect data signals from sensors like heart rate, skin conductance, movement, voice, or facial expressions. The second step is pre-processing. So this step cleans the data. Many physiological signals are quite noisy. So for example, when someone moves their arm, the heart rate signal can be distorted. Then the third step is extracting features. Features capture important patterns. For example, in speech, a feature could be pitch. For physiological signals, a feature could be heart rate variability. After this, a classifier predicts the emotional state. So that's the fourth step, which is classification. It may predict states like stress or calmness or engagement. Some systems include interventions. So that's the fifth one. So, for example, a breathing instruction in a stress detection app is an intervention. I want to highlight something important here. Every step has difficulties. Noise in data can reduce accuracy. Wrong feature extraction can hide important signals. Even the model itself can behave differently for different people. So, this pipeline helps us understand how complicated emotion recognition actually is. There are many layers where errors can appear. So, the main contribution of this paper is the design space itself. So, the paper does not propose any new algorithms, it does not introduce new sensors. Its value comes from the way it organizes the field. The design space includes four parts. The first one is theoretical models of emotion. Second, platforms where emotion recognition is used. Third, sensors and data sources. And finally, the fourth one is applications that use these technologies. The paper also highlights ethics and privacy concerns. These are often ignored in technical papers. So, the strength of this contribution is that it gives structure to a complex area. It helps us think clearly when designing an emotion recognition system. So, emotion recognition starts with understanding what an emotion is. So, the paper reviews three major models. The first one on the top is the Aikman Basic Emotions. It describes emotions as categories such as happiness, anger, sadness, etc. It is simple and easy to understand. The second one is the one on bottom right, which is the PAD model. So it describes emotions using pleasure, arousal, and dominance. This helps us represent emotions that do not fit strict categories like happy, sad, angry, or scared. And the final one and the third one is the Geneva emotion wheel, which is on the bottom left. It shows emotions in a circular format and includes intensity. So these models show that emotions are complex and personal. For example, two people may show sadness in different ways. Culture also affects expression. This makes emotion recognition more challenging. It is not recognizing objects, it is not fixed. So the choice of the model also affects how data is labeled. This is important because the truth labels influence the final accuracy of any machine learning systems. Finally, the paper talks about platforms where emotion recognition systems may run on. So, smartphones can collect data all day. They can sense movement and record speech. Wearables collect physiological signals. Wrist wearables are comfortable. Chest bands collect stronger signals but are not as comfortable. Robots can detect facial expressions during interaction. VR or virtual reality headsets track detailed movement and can also deliver interventions. Cars can sense driver stress using sensors in the seat or steering wheel. Each platform has its own trade offs. For example, a smartphone is convenient, but it may not sense accurate physiological signals. A chest strap is accurate, but many people may not want to wear it daily. So, the choice of the platform influences the quality of the data and real world usefulness of the system. So, this is one of the largest parts of the design space sensors and data. So, the paper reviews many different types of signals. Physiological signals include heart rate variability, skin conductance, EEG, and FNIRS. These signals reveal arousal and stress. The movement data reveals body posture. Posture often reflects emotional states. Facial data shows expressions. It can be collected using a camera or electrodes placed on the skin. Speech signals carry emotional information. Stress can change pitch, tone, and speed of the speech. Environmental context finally gives us useful clues. People behave differently depending on the time of the day, temperature, and location. Many systems use multiple signals, for example, combining heart rate with speech. Multimodal data often produces stronger results but increases complexity. It also raises practical issues. So, more sensors means higher cost. Users may not want to wear many devices. So, data storage also becomes more expensive. Balancing accuracy and practicality is a key challenge. The paper also discusses common machine learning methods used in emotion recognition. Support vector machines and decision trees work very well with small data sets. They are simple and fast. Nearest neighbors and random forests are also used often. Neural networks can learn complex patterns, but they require a lot of data. Emotion data sets are usually small and noisy, so classical methods are still common. One issue the paper points out is that many studies use limited evaluation methods. This makes it hard to compare results. Better benchmarking is needed for the field to progress. Emotion recognition appears in many real world applications. In mental health, it helps detect early signs of stress or depression. In education, it identifies engagement and frustration levels. These signals allow learning platforms to adapt in a personalized way. In driving, it can detect stress or anger. This is important for safety. In assistive technology, emotion recognition helps design supportive interactions for users with communication challenges. These applications show the broad impact of emotion recognition. It can make systems more adaptive and supportive, and finally, more responsive. Emotion recognition still faces many challenges. Accuracy is a major issue. Emotional expression varies widely between people. So, models trained on one group of users often do not work well for others. Sensor quality is also inconsistent. Wearables can be noisy. Cameras rely on lighting. Speech quality changes with background noise. And finally, cultural differences influence how people show emotions. For example, some cultures show less facial expression even when emotional. Privacy concerns arise because emotional data is sensitive, and energy constraints affect wearable devices. High sampling rates look good in lab experiments but do not work in daily life. So, all of these issues combined make emotion recognition quite difficult. They show why strong general solutions are still missing in the field. Emotion data can reveal very personal information. It can reveal stress, frustration, or sadness. It can even hint at mental health conditions. Continuous sensing might record data without user noticing, and some systems store data in cloud platforms. This just increases the risk multiple times. There is also the risk of emotional manipulation. For example, a system might suggest therapy or medication without the user asking. So the paper argues that emotional systems must be transparent. Users must know what is collected and why is it collected. It also stresses the need for minimal data collection. Systems should collect only what they need. So this connects to broader discussions in responsible AI. So the strengths of this paper come from its structure. It organizes a very large field in a simple way. It brings together theory, sensors, platforms, and applications. It includes a discussion on ethics and fairness. It is very useful for students and designers entering the field newly. It gives clarity in an area that is often very confusing. The paper also has clear limitations. It obviously does not include any experiments. It is just a review paper. So the design space, however, is descriptive, but it does not test or compare different combinations. It does not include benchmarks or standard evaluation metrics. It does not discuss deep learning models in much detail. These models dominate current research, and in spite of that, going into not much detail is a huge limitation. Another limitation that the paper does is it does not address the reproductibility crisis in effective computing. Models often fail when used on new users. So, this paper acknowledges this but does not explore solutions. So, because of these limitations, the paper is better as a conceptual guide than a technical contribution. There are many ways to improve emotion recognition. We need larger and more diverse datasets. Many datasets today come from small or homogeneous groups. We also need personalized models because emotions vary a lot between people. A one size model does not work. Privacy preserving approaches such as edge processing can reduce risk. So, we need clear evaluation standards so that results can be compared. There is also a potential for combining physiological data with modern language models to create more natural and adaptive interactions. Future work must also focus on fairness and accessibility. Emotion recognition should work for everyone. So, in conclusion, emotion recognition is promising, but it's very challenging. So, this paper provides a helpful design space to organize the field. It encourages careful thinking about theory, sensors, platforms, and ethics. It also highlights the gap that remain in accuracy and generalizability. Although the work is conceptual, it is valuable for guiding future research. So, thank you for listening.